Hey everyone, and welcome. Today, we're jumping into a really cool story from the world of digital signals. It's basically a tale of two tools, two fundamental operations that seem like they're complete opposites, but you'll see, they work together to shape so much of our digital world.
So let's start with a puzzle. Just think about it for a second. How is it possible that we can take a digital signal and use it to do two totally opposite things? Like sharpening the edge of a photo to make it crispier, and then using a similar process to smooth out the hiss from a music track. One's about adding bite, the other's about making things calm. How does that even work?
Well, the answer, as you probably guessed, comes down to these two core concepts. You can almost think of them as the yin and yang of signal processing. One is all about looking for sudden, dramatic change, while the other is focused on accumulating things slowly over time. So, let's meet our first character in this story.
All right, first up, the differentiator. If this tool had a personality, it would be, kind of impulsive and excitable. It's obsessed with what's happening right now. Its entire job, its whole reason for being, is to detect change.
Okay, so the technical definition says it approximates the derivative. But let's just push the math book aside for a second. All this really means is that it's designed to listen for any part of a signal that changes super fast. It pretty much ignores anything that's steady and just amplifies the spikes. It basically shouts about them.
And here's the perfect way to picture it. Imagine you're at a baseball game. You've got that constant low hum of the crowd, right? That's your baseline signal. A differentiator just lets that fade into the background. But that sharp, sudden crack of the bat hitting the ball, whoa. That's a moment of incredibly rapid change in the sound wave. The differentiator locks onto that and makes it stand out.
So, where do we actually use this thing? Well, a ton of places. In image processing, the edge of an object is really just a rapid change in color or brightness. The differentiator finds those edges to make the image look sharper. For a security camera, it spots motion by noticing when pixels change really quickly from one frame to the next. It's all about pinpointing those critical moments of transformation.
Now let's meet its polar opposite. This is the integrator. And if the differentiator is all about that sudden spike, the integrator is more like a patient historian. It's carefully gathering information over time, always focused on the big picture.
So the integrator's whole job is to sum things up. It looks at the value of a signal at every single moment and just keeps adding it to a running total. And the effect of all this accumulation? It smooths out any of those sudden, jerky movements in the signal. And instead, it reveals the overall trend.
This is the perfect contrast to our baseball game analogy, isn't it? The integrator couldn't care less about that one intense cloudburst that happened on a Tuesday. Nope. Instead, it's collecting a little bit of data every single day to give you the total rainfall for the entire month. It's all about the cumulative result, not the fleeting, momentary intensity.
And you can totally see this in where it's used. You know that annoying high-frequency hiss you sometimes hear in an old audio recording? That's really just a bunch of rapid, spiky changes. The integrator just smooths them right out, leaving the nice, clean music underneath. It's also used in control systems, to make sure a robot arm moves smoothly, instead of in a bunch of jerky steps. It's the ultimate smoother outer.
Okay, so we've met our two main characters. One detects change, the other accumulates it. Now, let's put them head-to-head and really see how they stack up against each other.
This table just lays out the core conflict perfectly, doesn't it? The differentiator wants to find that derivative, those sharp, sudden changes, which is great for things like finding edges in a picture. The integrator does the exact opposite. It accumulates the signal over time, which is exactly what you want for smoothing out audio noise. You can see they are fundamentally opposite goals, and that leads to completely opposite effects.
So if you remember one thing, let it be this. It all, and I mean all, boils down to this simple idea: detection versus accumulation. That is the fundamental difference that lets them do such wildly different things with the very same kinds of digital signals.
Okay, let's get just a little more technical for a sec, because this explains the how. A differentiator basically acts like a high-pass filter. Think about it, those rapid changes we talked about are high-frequency events. So of course it lets them through and even gives them a boost. The integrator is the reverse. It's a low-pass filter, favoring the slow, steady, low-frequency parts of a signal. And that's exactly why one is great for sharpening and the other for smoothing. Of course, neither is perfect. They both have their own challenges, like instability or tiny errors that can add up over time. So, they're opposites in pretty much every way you look at it. But what if I told you they're actually deeply and fundamentally connected?
They're not just rivals in our story, they are literally two sides of the very same coin.
And here it is. This is the big reveal. Remember how we just said a differentiator amplifies high frequencies? Well, guess what? That's exactly what a high-pass filter does. And the integrator, which amplifies low frequencies, it's just behaving like a low-pass filter. So these aren't two separate magical operations. They're just the practical application of basic filtering principles.
So, what's the big takeaway here? It's that these two ideas, detecting change and accumulating a total, they're not just some abstract math concepts. They are the essential, fundamental tools we use every day to shape signals, whether that's to make a picture clearer, a sound cleaner, or a robot's movement steadier. They're the basic building blocks of it all.
And that brings us to the end. So I'll just leave you with this thought. This pattern, this battle between immediate change versus long-term accumulation, it shows up everywhere, way beyond just signal processing. Now that you see this fundamental pair, where else are you going to spot it? Thanks for tuning in.